does this represent in the system of linear equations? It represents that 0 times x1 plus 0 times x2 plus 0 times x3 equals b3 plus 3b b1 minus 1/2 b2 plus 2b1. And combine these together. You notice I did the simplification. That's all I was doing right there. So I simplified this issue. So AX equals B. And you'll notice if you pick B1 and B2 to be arbitrary, then this gives you a constraint on B3. So you can figure out what B3 is based on B1 and B2. So AX equals B has a solution if and only if this holds. If and only if this is true, B1, B2, B3, yes. What is your name, by the way?
Trey.
Trey?
Yeah.
Okay.
This is just computational. Is the B1 supposed to come out to a 1 or a 5 at the end? Okay.
Very good point. I did that on purpose to see if anybody was paying attention. Yeah, so we have this equation right here, and it tells us if this has a solution or not. Which also tells us that it is possible to have a set of 3 column vectors that there are things not contained in the span of these vectors, right? It is possible to find vectors that are not in the span. It's possible to find AX equals B that does not contain a solution. What's an example of a solution? Well, what's an easy example? Pick B1, B2, and B3 that satisfy this. What's a possible choice for B1, B2, and B3?
All zeros.
All zeros. That works perfectly. 0 plus 0 minus 1/2 times 0 is definitely equal to 0. All right? So we know that 0 is in the span of 1 minus 4 minus 3, 3, 2 minus 2, 4 minus 6 minus 7. 0 is in the span of these things. We knew that from last time though, right? We did specifically say 0 is always in the span. So, yes, the vector, I'm writing this is the vector 0. No matter what vector space we talk about, we always have this vector 0, 0, 0. It has this nice property that if you add it to anything, it doesn't change that thing, right? It's a 0 vector in that vector space. Now, we have another property that's nice about it. It's in the span of everything. No matter what vectors you pick, the 0 vector is always in the span. Can you give me another example?
1, 4, 1.
So 1 minus 1/2 times 4 is 2 minus 2 plus 1 is equal to 0. So now we have another example of something that's in the span. 1, 4, 1. That's also in the span. Yes?
So does that mean that the solution's not unique because we have different things that could be for the vector x, right? Because it was 0 and now it's 1, 4, 1, so the solution's not unique.
This is not the solution. B is equal to this. If we pick this as B, so this is our choice of B, then there is a solution. Based on all this computation that we did right here, we found that B does satisfy this relationship right here.
So it's just saying that there are many different choices for B that can get a unique solution.
Yes. Yeah, we will have, in this case, we will have a unique solution based on what B is. But there are other vectors, for example, 1, 1, 1. This is not in the span. So, not in the span of this. And so for this, there's no solution. If there is a solution, remember that it was either unique or there were infinitely many.
So the augmented matrix, we did AX equals B. Yeah, that's right. And we've got A is that, we've got B is B1, B2, B3. So when we've got a system of equations, it's like X plus Y plus Z equals 1, and then 2 more lines like that. When we write that matrix, we write it as 1, 1, 1, negative 1, right? Because we gotta bring it to that side before we do 0, or we write it as 1, 1, 1, 1.
The second one.
Okay.
1, 1, 1, 1. Because if we look at a system of linear equations, and this is a very important question, if we look at the system of linear equations in the standard form, let's say x plus y plus z equals 1. And we're calling this the first variable, the second variable, and the third variable. Yeah, the row that represents this in the augmented matrix is 1, 1, 1, 1.
So when you do the line between them, then it's negative 1 on the other side or something.
No, we could go either way. We picked a convention on which way we're going to go.
Okay.
We're going to say that this is the standard form.
Mm-hmm.
The variables are in whatever order we specify,
Mm-hmm.
this alphabetical order in this case, equals some number.
Okay.
So on this side of the equation, we have a linear combination of x, y, and z. 1 times x plus 1 times y plus 1 times z, right? Here I'm thinking of these as just numbers, right, not vectors. But it's still a linear combination, right? I'm multiplying them all by scalars, I'm adding them all together. And the other side is what the linear combination of those things is. This is the standard way this is the standard form that we picked by convention. Now for any particular reason, the standard form could have been this if people liked that. Turns out people didn't like it that way, they liked it the other way. And now we're stuck with it.
So this is why I repeatedly tried to throw my laptop across the room and realized it'd be better to throw my clipboard instead during my homework.
Clipboard's cheaper.
Yeah, it confused me a little. Yeah, dollar store clipboard, Mac store laptop.
Easy choice.
Yeah.
So this is the standard form, and to get the augmented matrix from the standard form, we just read it off,
Okay.
entry by entry. We have to all be speaking the same language, and this is our language, right? Once we've done that, everything is okay. Right? But first of all, we have to be speaking the same language. All right, so that's that. We have 8 minutes left. Important I come to a point about this. And that is when is it the case that any B is good? Any B works. So when does AX equal B have a, this is one of the central questions in our study when does AX equal B have a solution for any B, which is B1, B2, up to Bn, belonging to Rn? When is this the case? And remember, I'm going to write A as column vectors, A1, A2, AK. So first of all, we're assuming that based on this, X has to be equal to X1 to XK, has to be a K by 1. We're assuming from this that AX equals B is actually defined. Okay. Well, when does it have a solution regardless of our choice of B? Well, what went wrong here? What went wrong in this example?
It all came to 0.
It all came to 0, exactly. Yeah. So, if at the end of this we had a 1 here instead, we could have continued with the row reduction algorithm to clear out these entries, and then got a 1 here and clear out these entries. And at the end, we would have got x1 equals something, x2 equals something, x3 equals something, and we would have got our solution, our unique solution. So we have a bunch of different equivalent ways of saying that AX equals B has a solution regardless. Well, first, the first way to say it is what I just said. AX equals B has a solution regardless of B. I'm just stating. What's an equivalent way to state that? Number 1. B is a linear combination. It is a linear combination of A1, A2, up to AK. Make sense? What we said before, B has to be in the span of the columns of the matrix A. So that's the first way of saying that, other than just saying it. Another equivalent way to say it. I'll hold the book, save this. Yeah. The span of A1, A2, A, this is the set of all linear combinations of these columns. If every B is in it, if every n-dimensional real vector B is in that span, then the span is actually exactly the same as Rn. Yes?
Could you basically state what you said at the top, where you get any solution B is if you can put AB into reduced row echelon form, then any B can be picked?
Number 3.
Yeah.
And this is the final way that the book gives. But there are other statements as well. When we get to the talking about the determinant, there's another statement as well that's really useful. But this is what he said. How's the book? Let's say it our own way. The augmented matrix A, B, and coming back to your Connor, is that right?
Yes, sir.
Okay. Connor, coming back to your point, I'm just not writing the line here. The line is just there for our convenience. It's just to indicate to us that it's an augmented matrix.
Okay.
It's not necessary. This is just a matrix.
Okay, so the line doesn't actually change. If I see the line in something or don't see it, it doesn't change.
Yeah, exactly.
Okay, except whether I have to hit tab an extra time when we're doing the homework to get past the one, sorry, on the end.
I know what you mean,
Yeah, okay.
I did the homework myself last night, so that I would go through the same suffering that you are. And it was suffering. I have decided that if I'm gonna do big computations of big matrices on the exam, that's gonna be during the part where you're allowed to use calculators.
Yeah, it takes a lot of paper.
Yeah, exactly. So, I should come back to that. So the augmented matrix AB has a pivot or pivot location in every, they say row? Yeah, they would phrase this as every row. So in this case, we had a pivot here, a pivot here, and this was a 0, and we were on the last row and there's nothing left to do, so we didn't pick a pivot. Right. So there was no pivot in this last row, which is what you said. After
Reduced row, I said if you can.
reduce, yeah, sorry, go ahead.
So if you can put it in a reduced row echelon form, so 1 0 0 0 1 0
Yes, this is a good point. I didn't let you finish. What was the last part of your statement?
Then B can be any combination of B1, B2, B3 will work and have a solution.
Yeah, that's true. Now, the first part of it said, you said if you can put it in reduced row echelon form. And this is an important point. Every matrix can be put in reduced row echelon form.
Okay.
The form just may not give solutions,
Okay.
but every matrix can be. We can always do this process. And that's an important point. Like,
Okay.
we can always, this is reduced row echelon form.
I guess I meant to say if you had a pivot in every section with every other term being 0,
Yeah.
is a better way to put that.
Yeah, exactly. And that's exactly correct. Yes?
In the book, after that, it says, this refers to a coefficient matrix, not an augmented matrix. That's the difference.
Same as a pivot, is it in every row?
Anybody in here?
Well, then let's state this. I guess what that's saying is that we could have picked this as a pivot. Yeah, that could have been our next pivot. No, that's a good point. Okay, so what have we missed? We have missed today what is in section 1.4. We won't always have time to go through everything in this section in class, which is another reason why it's really important to read this stuff. But, yeah, that's it. Just read this section. What we didn't get to is a way of computing this product AX. Be sure to read that in the book because I'm going to assume that you know it next time. Also, is anyone planning to come to office hours? Good. My office mate is, it sounds like he's sick. Email me this concern. Take care of it. Because if I try to remember it.